right, hello, Red Wing Chemistry geniuses. I hope you had a great long Valentine weekend, and we are going to basically finish up our lecture, our whole unit on doing these mathematical conversions that deal with the mole. But today we're going to hit a little bit harder of actually defining what a mole is and how that has become to be part of chemistry. So let's go ahead and get started from the beginning. All right, so the mole. Biologists might think of this cute little guy. Some people have made arguments that a mole is cute. When they're in my backyard, I think otherwise. Not many people think this mole is cute. This is this is the real name for this mole. This is called the poop-eating naked mole rat. All right. Anytime you have poop eating in your name, it's not a real good lifestyle. But I will say this, that the poop-eating naked mole rat gets a bad rap, but it is a very fascinating creature. It has no pain sensors, which is very unusual, even in simple one-celled organisms. Some of them have a way of detecting pain. And it's also a cold-blooded mammal, which, of course, very, very rare. This little guy might save your life someday, because they have found that these organisms are extremely cancer-resistant. Excuse me. It was thought for a long time that they actually never got cancer. But they had such a good defense that they had to research with them and expose them to a lot of different cancers before even just a very few of them got cancer. They have a very good system for fighting cancer off, and it's helping a lot with resistance. They're also a social animal, much like bees. If you think of bees with the queen, this picture right here is a queen poop-eating naked mole rat. And she earned that by fighting off another queen and penetrating those nice teeth that she has there through the lungs of her competition. So, not the nicest little creatures, and not the best looking, but some very interesting. So don't be too fast to judge the mole. All right. So it's not that kind of mole. We're not talking about that kind of mole. We're not talking about the mole on the face, like that mole right there. This is from the great movie Uncle Buck, where he finally says to this woman who's being very rude to him, "Here's a quarter, go downtown and have a rat gnaw that thing off your face." When he first meets her, you might have seen the movie, he said, "I'm Buck Melanoma. I'm Molly Russell's wart." Not her wart. She's my tumor. I'm her growth, her lesion. Her uncle. It's kind of a funny scene. Anyway, it's not that kind of mole either. Not a face mole. So, it's not a spy mole. You've probably heard that term used there. It is a chemistry mole. So, you guys kind of know what this is because you've been writing grams per mole a lot. It's that many grams per 1 mole. But exactly what is that? And to use that, we're going to use this. Here are some things that you're very familiar with. 1 pair of socks equals 2 socks. Stay with me. 1 dozen eggs. How many eggs? 12 eggs. Now, if you have a mole of gold, all right, how many would that be? It's not 2, it's not 12, it is 602 sextillion atoms. Now that is a big number, all right? So a mole, you have to think of being this super huge number of anything, really. But we usually reserve it for the really small stuff. So let's try to conceptualize what 602 sextillion is, all right? Well, first of all, you got to look up and see what sextillion is, and that is sextillion. It's kind of interesting. The prefix sext, which has a different meaning now, means 6 in this context. And you look and you're like, well, there's like 7 groups of 0. Well, you don't count the first one because that's just a normal 1,000. So really, it's at 10 to the 6 and a million. They call that 1. A billion, that's, think of it as being 2. Bi, might never have thought of that. And 3 trillion, probably never thought of that either. And then you get into quadrillion, quintillion, sextillion. All right. So in other words, you've got 21 zeros up there. So it's 602 with 21 zeros behind it. Just a really big number. All right. So to try to put this in some sort of context, we'll use a couple of examples here. It's basketball season, March Madness, not that far away. What if you had a mole of basketballs? Well, interestingly enough, a mole of basketballs, and this has been calculated, if you had a mole of basketballs, it would make a sphere of basketballs. Think of that as a big giant sphere of little tiny basketballs, and it would be the size of the planet Earth. Now, you just think how big the planet is, and that's a lot of basketballs. And volume-wise, we're talking all the way down through the, in the core and the mantle and right to the very inner parts of the whole planet would be basketballs. And that's a mole of basketballs, which you could have, because you could have a dozen of anything, right? You can have a mole of anything too. What about a mole of dollars? This one's always interesting. So that would be a lot of money. Let's find out how much money that would be. So let's say somebody today, for a present for you, a little late Valentine's Day present, they put a mole of dollars in your bank account. All right? So you look in there and you're like, oh, good, I got a mole in there. That's a lot of money. And so firstly, send them a nice thank you card, because this is going to be a life changer for you. And here's why. You could spend $1 million a second for the rest of your life. Okay? And then, when you were 100 years old, you would still have 99% of the original money in the bank. All right? You're spending $1 million a second, and you still have most of the money in the bank after, what would it be for you guys, about 83, 82 years. That's a pretty impressively large number. All right? And the bottom line is, it just doesn't make sense in our world. One nice thing about this, that money would actually be tax-free, because this is a hypothetical example. There's no real money. You're not getting it. So you don't have to pay taxes on something you never got. Hypothetical use for educational purposes only. No tax. So that's the good news, I guess. So we use this number all the time with little tiny things like ions and molecules and formula units and atoms. So we don't want to always have to write out all those zeros. yeah, you get to round plus or minus a couple of sextillion. But we do need to work with those numbers, including in the worksheet that you're going to be doing tomorrow on doing these calculations to get ready for the test, which is coming right up on Thursday. That's a really big number. But now here, look at this. If you have a mole of water molecules, which you probably got several moles sitting in your water jug right now, that would only equal about 1/3 of a cup of water. So that shows you how small those molecules are. Because, you know, if those were basketballs, if those molecules were changed to the size of basketballs, that cup would have to be the size of the planet Earth. So it's really quite amazing how big a mole is and how small these particles are that we're dealing with. All right? So we don't write the number like this. That's too many zeros. It just gets sloppy. But we deal with it all the time. So what we do is we use scientific notation. Okay? And that just makes a lot of sense. 6.02 times 10 to the 23rd. And that's the way that we will talk about a mole of atoms or formula units or molecules using this sort of notation for it. Okay? And one of the things I'd like you to note here is there's no unit behind there because we can't have one. It's like having a unit behind a dozen. You're like, a dozen what? Donuts? Sounds good. Eggs? Sort of boring. You can put anything behind a dozen. You can have a dozen of anything. You can have a mole of anything. But it doesn't make very much sense in the macroscopic world. So we use it all the time in chemistry. So let's talk a little bit about the history of this number. It has been coined Avogadro's number, who came up with some really important ideas very early on. Actually, in the early 1800s, he had these ideas of, hey, the particles in these things, we really have to be able to figure out a way to count particles. And they're like, you can't, they're too small. And they were right, but so was he in postulating an idea that these things, so Avogadro became very famous for that. I'm not sure what's more flattering, his real picture there or the caricature. I kind of like it because it's got the balloons, and that's kind of what he did, is he studied gas molecules and said, in theory, these will occupy the same space at the same conditions, no matter what gas they are. And that is spot on. And it was very early on that he decided that. So he definitely deserves this. But he died not getting any credit, like many scientists at the time. People were very, very skeptical about things. Does that sound familiar? Some people skeptical maybe about vaccines and things like that. And it's natural for us to question things, but sometimes you just gotta trust the scientists. And in this case, Amadeo Avogadro was correct. All right. Now, in defining this, we take one of the most common atoms, and this is how they came up with the number 6.02 times 10 to the 23rd, is they took carbon, because carbon's in so much stuff, right? And they did some estimations and the basic size of the atoms and some calculations. And remember, we're talking about plus or minus, a couple of sextillion there. So it's not a super accurate number, but it has 3 sig figs, and that's what we use for our calculations. So it's definitely going to work for us. But they said, let's take 12 grams of carbon-12. Kind of arbitrary, but it's carbon-12 is the one with 6 protons and 6 neutrons, and that is where that magic number came from. I'll see you on video number 2.